Okay, in this little lecture, we're going to just talk briefly about how we can relate the rate constant to the delta G double dagger, the activation energy. So let's consider a reaction where we're converting substrate to product. Okay, we could write an equilibrium expression for the equilibrium constant for that. It would be the concentration of product divided by the concentration of substrate. Then we could say, well, the free energy for that process, the standard state free energy, is minus RT natural log KEQ. And we know that as you increase KEQ, delta G naught becomes more negative, which is a more spontaneous reaction. It's a reaction where the equilibrium position has more product than reactant. But it tells us nothing about how fast the substrate gets converted into product. If we wanted to know something about the rate of that conversion, we know that it would be the rate constant for the forward reaction times the concentration of the substrate. In this case, K1 is a first order rate constant because it depends only on one reactant. There's only one reactant in this particular example. So what we want to do is we want to now relate little k to delta G double dagger in much the same way that related big K to delta G naught. And the way that we do this is we use something called transition state theory. So in transition state theory, what we do is we ignore everything about how molecules collide. How they collide is irrelevant. All that matters is the reactant and the transition state. And it's important to remember that the transition state is not an intermediate. It's a peak in our reaction coordinate diagram, not a valley. So intermediates are valleys in reaction coordinate diagrams. The transition state, substrate to product, this transition state up here, that's a peak, okay? So we know, we're going to do some transition state theory here, that the difference between the substrate free energy and the free energy of the transition state, we know that that's the equivalent of the activation energy, delta G double dagger. But we could also say that there is a thermodynamic equilibrium between the substrate and that transition state. And there is an equilibrium constant that describes that equilibrium. So we could say delta G double dagger then is equal to minus RT natural log of that particular equilibrium constant, where that equilibrium constant describes the relationship between, or the ratio between the concentration of the transition state and the concentration of the substrate. So then we could just do a bunch of math. So normally I derive this, but I'm not sure it does anybody any good. So I'm not going to do that here. So if you want to see how that happens, you could come by my office. But in the end, we can derive this relationship between the rate constant and the activation energy. So the rate constant is equal to the Boltzmann constant times the temperature divided by Planck's constant, e to the negative delta G double dagger over RT. Okay, so what we see here is that the lower the activation energy, the greater the rate constant, and the greater the rate constant, the faster the reaction rate. So this should look a lot like this equation K equals A e to the minus EA over RT, which is the Arrhenius equation, where A now is the Arrhenius constant. And this is how we derive the same expression when you were in general chemistry. But now we have two relationships, one that relates the rate constant to the activation energy, and then our standard one, delta G naught equals minus RT natural log big K, which relates the thermodynamic free energy change to the equilibrium constant.